It.
1 second, just looking for the button.
Oh.
Okay, here we go. Hello, everyone. My name is Nick, and today I will be presenting the work with Federico Mora, Vincent, Marsha, Chechik on the topic of scaling client-specific equivalence checking via impact boundary search. So first, let's talk about the problem. The problem of client-specific equivalence checking is first asked by us in our paper at ASE2020. In the problem, we have a system denoted as the client. Client calls an underlying component called the library. Suppose there's an update to the library. We want to check if the update impacts client or not. In our old paper, we proposed a solution and implemented a tool called Clever. Clever takes in a client and two different versions of the library. And it will say the two versions of the library are client-specific equivalent, meaning that client's not impacted if they're not impacted. Otherwise, it will say not equivalent. Clever and the old solution worked very well for the benchmarks, for the set of benchmarks selected and studied in our old paper. However, it has its own drawbacks. Let's see the weakness using this motivating example. In this example, we have a client, some primes, and two different version library, composite old and composite new. The client tries to sum up all the prime numbers up to the input x. And in one of the loop, it calls the library to see if the input j is a prime number or not. The old version of library returns a number of factors of the input num, and the new version of the library returns 0 if num is a prime, and 0 and 1 if otherwise. So if we feed this problem into our old tool Clever and give 600 seconds timeout, Clever couldn't terminate. We also tried this problem on other general equivalence checker. Unfortunately, we tried on rep, modif, simdiff, RVT, and unfortunately, none of those equivalence checkers can give us the answer. They either say they don't know or they couldn't terminate. They all struggle on this problem. And why? So after a close inspection, we realized under this problem, the equivalence checker usually produce very large queries that are kind of hard for their reasoning engine to handle. Some techniques are pass-based, and unfortunately for this problem, there are just too many passes. And some techniques based on invariant inference techniques, but it's quite expensive for input like this, like the input we have right now. So let's take a closer look at the instance sum prime and understand why it's hard for those checkers. So if we look at the client calls the library in an unbounded while loop. And the library also has an unbounded while loop on its body. And if we compose those two programs together, the double nested loop structure makes reasoning extremely hard. But fortunately, a lot of the time we don't have to check the entire program, especially we don't have to consider entire client to understand equivalence. In particular, we can only look at the portion of the client considered as the client context, and maybe under this client context, the two library will behave the same. Unfortunately, that's the case in this instance. The client calls the library and use the result only to compare against 0. Even though the two versions library behave differently and have different results, but under this client-specific client usage, client context, they behave exactly the same. So this is the key. We want to look for client context. So suppose we have two version library and the client context. We can encode the problem only with the client context. And we can throw this assertion into a verification tool. And if the verification is successful, we can say that under this client context, the difference in the libraries are being successfully mitigated. And this gave rise to our new approach, which is search and check relevant client context. So this motivated us to design our new approach. We call it Too Clever. At a high level, it takes in client and two version library. And the way it does is try to decompose the client and try to find the different relevant set of client contexts And if we find one context that is sufficient enough to prove that the difference in library are successfully mitigated, we got the result of equivalence. And yeah. So let's take a closer look at the detail of 2Clever. The client contexts we're searching for, we give them a name called the candidate impact boundary. Candidate impact boundary represents an extractable subprogram of the client that contains the library call. So on the example on the right, we see the library call site itself is a candidate. The expression in the if is also a candidate. The entire if construct is also a candidate. The body of the while loop is a candidate. The while loop itself is candidate, and so on. And the largest candidate of the client is the client itself. So more specifically, a candidate impact boundary is a subprogram that has a single entry and has a single exit. The single exit condition can be relaxed since we can transform program with multiple exits into an equivalent program with single exit. The third condition is that every non-local path to the library call site must go through the entry of the candidate. By non-local, I mean a path that has the step outside of the candidate. So what's so nice about the candidate impact boundary? If we can show that the candidate impact boundary is client-specific equivalent, then we show that the library's impact has been mitigated, which implies that the entire client is client-specific equivalent. We call such candidate impact boundary a true impact boundary. But the problem is we cannot check all possible candidate impact boundary. There are just too many. We have to choose which one to consider and how can we check them. So in practice, 2Clever considers 3 types of candidate impact boundary. We identify those candidate impact boundary by analyzing the control flow of the input program. We transform the program into a control flow automata and perform analysis on them. The first kind of candidate impact boundary is the library call site. Since it's the smallest possible candidate, we find the call site, we extract the impact boundary, and show on the right as well. The second type of candidate impact boundary we're checking is cycle broken candidates, which represent the largest candidates without including a new cycle. To see that, we first analyze the control flow of the program. We identify cycles. Then we try to find the last candidate inside the cycle and break the cycle by removing the back edge. The third type of candidate is the entire client. We need to have the client as a candidate to ensure our approach is complete. So if we consider those 3 types of candidates, a nice property we can have is that those candidates naturally form a hierarchy with subprogram relationship. In our case, candidate 1 is a subprogram candidate 2, candidate 2 is subprogram candidate 3. And we can check them in the inside-out order. We check 1, and if it's not a true impact boundary, then we check 2. If 2 is not true impact boundary, we check 3. And the reason why we consider the cycle broken candidates other than other type of candidates is because we think that to reason, like difficulty usually come with reasoning is the presence of cycles. And if we have the ability to avoid reasoning of the cycle wherever possible, we should do it. So let's put our approach into practice. Suppose right now we're checking the cycle broken candidate at this moment. Well, 2Clever will transform the candidate into a standalone function, and then try to check if this function with the 2 version library are client-specific equivalent. At this point, we can use any equivalent checker, and we also develop our in-house checker to exploit the problem structure. What we do is we apply self-composition and try to assert that at the end, the 2 states, when they return, they have the same return value. If at this point, if the check result is successful, we show the call site has no impact on the client, then we're done. On the other hand, if we show that the candidate is not a true impact boundary, then we have to check the next one. Before checking that, we can refine what we have done before into a standalone function and put them into the next candidate, then check the next one. So the algorithm, as illustrated above, is quite simple. What we do is for each library call, we try to search for the smallest possible candidate impact boundary at this moment and check if the candidate is actually an impact boundary. If it is, then we are done with this call site. We can move to the next one. If it is not, then we have to check the next candidate. The algorithm will terminate and conclude equivalent if every library call site has an impact boundary, and will conclude not equivalent if some library call site has no impact boundary and some candidate cannot be refined anymore. Intuitively, why toClever is beneficial? First, check the client context. The candidate impact boundary is instead of checking the entire client, is asking a much easier question. Second, if we find such candidates, the candidate explain why the library call does not affect the client. Third, whenever we conclude that the current candidate is not impact boundary and have to check next one, what we learn from the current candidate candidate can be reused during the check of the next candidate. So this allows us to do incremental equivalent checking with increasing client context. Lastly, because we have to do this for each client call, each library call, as long as the candidate impact boundary do not overlap, we can check them in parallel. So let's talk about the experiment results. The first question is, how does toClever compare against the state-of-art equivalent checker? To answer this question, we compare toClever with the state-of-art equivalent checker Rev, which is a general equivalent checker, but is capable of answering our problem, as well as our predecessor, Clever. For the benchmark, we select 40 instances from the related work, but we realize those 40 instances are relatively easy for all three equivalent checkers. In order to make a meaningful study, we want to have more harder instances. We generate those instances by by combining existing instances from the related work benchmark. We created 582 of them. For each instance, we allow 300 seconds timeout and 8 GB memory. And this is the results. As we can see, toClever has a bit of overhead from analyzing the control automata, but it scales very well. It has lead over Rev and Clever. Rev solved about 250 instances. Clever solved 389 instances. And only toClever solved 586 instances, 38 instances. The second research question we're interested in is, how does toClever scale with respect to program's worst-case runtime? To answer this question, we analyzed the experiment result and sort instances by their worst-case runtime. And this is the result. We group instances by their worst-case runtime complexity. We have 4 different brackets: constant, linear, quadratic, and higher order. First, we see that toClever outperform Rev and Clever in all brackets. And as the program worst-case runtime increases, the lead of toClever only increases as well. This suggests that toClever scale well with respect to the worst-case runtime. This might be explained by the way how toClever only considered the relevant client context instead of the entire client, so it's less likely to be affected by the worst-case runtime of the entire program. And there are more interesting research questions and analysis. For curious reader, please check out our paper. So let's conclude my talk with related work and summary. For related work, obviously, client-specific equivalent checking, the problem, we have done some pioneer work here. And they're also proving program equivalence, which is very related to what we have. And the other side of proving program equivalence is disproving program equivalence. This is like testing. And the regressional verification and incremental verification is also motivate our problem. So in summary, we find out that existing techniques usually struggle to scale on the client-specific equivalence problem, especially when the client has very complex, when it has very complex client. So instead of checking the entire client, what we're doing is we're looking for simpler but equivalent irrelevant client contexts. And checking equivalence on those simpler client contexts usually can infer the client-specific equivalence on the entire client. We implemented a tool called ToClever in Python and show it scaled well during our experiment. We also realized there's a lot of future opportunity. First, we can investigate how to pick candidates. And as right now, the way how we pick candidates to consider is quite, it's not optimal. We think there's a better way to do it. And then we also realized we are checking a lot of candidates and we can design a better parallelization scheme. So this concludes my talk, and I'm happy to answer your questions. The tool is available online. Follow this GitHub link. Thank you.
And so now, once again, I ask the 43 people attending to unmute and join me in a round of applause for our speaker. Thank you so much. And now,
hi, Tim. I think you are muted.
okay, so Nick, I'm embarrassed to say that this is not an area of my expertise, so I don't have a particular question. What was the biggest challenge in implementing all this?
The devil is always in the details. First, it's not very easy to extract the correct candidates. To make sure the candidate is sound, we have to ensure they have several properties. And to analyze the code flow and extract the right candidate is kind of hard. Sometimes we have to do a bit of program transformation to ensure that given an input program, we need to transform into an equivalent program so that we can extract the candidate. And this is a very interesting one. Another thing is when we are building our in-house checker, there are a lot of things to consider. For example, there's optimization we use for like lazy summarization of the client context. We also do self-composition, and also we did a bit of conditional model checking, which is when we have multiple verifier, when they have to, we define a way for them to give their partial result to each other. We did this through adding like program variables and the conditions so that like the one verifier don't have to repeat what the other one did. So with all this, like the result you see is actually the result of all the optimization plus our core technique.
Okay, so don't feel obliged to be industry relevant because we are primarily researchers. But if I ask the pathway from here to industrial application,
yep.
What would you say about that?
I think the problem is rarely relevant to industry, especially given that we have to we have API, we have a lot of like structure like client and the library, and library are typically updated faster than the client, and yes. The problem is relevant. And for our approach, I think the biggest challenge is to expand our language coverage to be able to handle more language construct and more data types.
Yes.
And one thing we did,
the language binding.
Yeah, and one thing we didn't handle is we couldn't handle like right at the moment we are kind of shy away from recursive program, and also the concurrent like the recursive program, and we couldn't handle concurrent program, and those are the two limitations we are facing right now.
Well, I think it's the mark of mature research to be able to state succinctly how far you've come and how much further you have to go. So I would call this very mature research. So if everyone could just unmute again and give a round of applause for our three speakers. Thank you so much to Nick, Xian, and Mohammed. And that concludes our session. Please enjoy the rest of ASE. Thank you for attending. Goodbye.